Hi, I'm Dirk Dusharme and welcome to Technorazzi. A few weeks ago we asked our viewers to tell us what they wanted to see. One of the things you told us was optical comparators. So we've gone back to CPM Labs in Rancho Cordova, California, where Craig Howell will give us the basics on using an optical comparator. Today we're going to talk about profile projectors, or optical comparators, or shadow graphs. These machines have been around since the 1940s, I believe. This particular model is an HB400, right, Craig?
Yes, it's a Starrett HB400. Very good, very sturdy comparator. 16-inch screen. The stage has quite a bit of movement. You can rapidly move it.
How are these normally used?
These are normally used to measure the profile or the shadow of an object. They're great for use on soft materials, rubbers, plastics, something that if you tried to physically measure with a micrometer, you'd bend it or distort it.
So what's happening here? A light is shining out of?
The light comes up through here, goes out through a lens, passes over the part and through a series of lenses and mirrors, and is reflected up on the screen. So we're measuring the shadow profile of the part in this case. We'll do our measurement by moving the stage. The numbers will read out here. And we also have a series on this unit of geometric forms. We can do a line, we can do a circle, distances, things like that.
Now in the old days we didn't have electronic display. Everything was actually done by
micrometers. We have micrometer heads on each axis. Then the next level up they just had a display that showed the X and the Y readouts. Now they have these to where they will actually, you can print them, you can send it out by way of a fax or an email. They're fully integrated.
And what kind of resolution or accuracy?
The resolution of the machine is 50 millionths per division. Typical tolerancing is 2 10,000ths per inch on the travels of the X and the Y.
Gotcha.
There is a tolerance on the actual projection, the power of the lens, a 20 power, a 5 power, 50 power, and we will set the lens to that in case you use a chart. If you're using a chart, the magnification of the lens is critical.
Okay.
If you're just going point to point, it's not as critical. But we take a lot of time getting the lens adjusted to really be 20 power or 10 power.
And what are you going to show us today?
Well, I've set up on a thread gauge just to show the shadow of the thread. And typically you could do a measurement where you would align, if you were just trying to find the major diameter of this thread plug, you would start off with it set right at the crosshair lines. You would crank it up until the other side comes right up to the line. And there we would take our measurement, and this one is 623 thousandths, 62395, just about 624 thousandths. That's how this is used on a thread. I'll set up on another example to show you some different features. Right now I'm going to put a round ball bearing up on the screen. You can measure the diameter of it by finding the largest edge of it. We'll align it to one edge and zero the display. Now we'll move to the far edge. Right about there. And we're showing 4995 500 thousandths right there. Right. This system has an optical edge detection feature on it, where you can set it up to where it's physically going to measure when the shadow crosses that path.
Okay. So rather than doing this visually, aligning the edge with one of these reticules here is this machine.
This machine can set up that direction.
Okay.
Now we're going to tell it we're measuring a circle. We're going to tell it circle. We'll just take a series of measurements. Circle takes a minimum of 3, and we always try to space the first 3 quite wide. I'll take a few more just for reference sake. And we'll press finish. And this tells us it's right at a ½ inch. Now this can be used for a number of things. You can measure distance from feature to feature. A very handy one is called skew. I really like skew. In the old days you had to line a part up manually to get it perpendicular to the stage travel. Now with the skew function, you'll see we're not sitting perfectly perpendicular. My shadow is off a little bit, it's skewed.
Okay.
So we can set this up We'll tell it we're going to do a skew. You take 1 point at one edge, at the leading edge we'll call it. We'll take 1 data point at the top. We'll move down to the other edge, which is not perfectly perpendicular. Take the second point and finish. Now the numbers are all skewed. Now we can measure a series of them in between and get a reading. In the old days we had to manually position the part square. This saves a lot of time. I use skew feature quite often. Angle is another nice function. We can see the angle this needle is sitting at by taking an angle measurement. First I'll take a series of measurements straight up, which will give us a reference line. Now we'll take the second series of them.
So you're just bringing the edge of the needle
to the crosshairs.
To the crosshairs.
And we'll press finish, it show us the angle. The second set on the needle. And this is the angle. That needle is sitting at a 7-degree, 13-minute, 55-second angle.
Oh, wow, okay. Okay, well, thanks, Craig, for showing us how to use an optical comparator on a real part.
Glad to do it, Dirk.